unlike the last section that was kind of, I don't know, it was kind of analytical. It was a little tricky. There were some details that were really important when we were working with those limits of those composite functions, and it got a little dicey, I'd say. This next section is pretty straightforward. It's very algebraic, and here it is in the title. We're going to be using some algebraic manipulations of our functions to find limits, what we call analytically, which I would say with algebra. So I'm going to repeat kind of the four-pronged approach that we're going to be taking year-long for this course. I call it the GINA approach. We are going to be looking at graphical situations. We've done that quite a bit already with limits. Numerical, with limits that would be looking at the tables, that's not the best. Analytically, which is what we're going to do right now with basic algebraic manipulation. And then we also are going to have a writing component, which we haven't hit quite yet, but it's coming in our continuity section this chapter. So we're going to get the full GINA already in chapter 1. But today we are going to, in this lesson, focus on some analytical methods for arriving at limits. Sometimes we use the graphical to help us analytically. So they're not all living kind of in their separate houses. Sometimes they kind of walk around, right? So the first thing here, you might say, I don't get what this means. This just means that if your function is itself a constant, because it says b is a real number, so in this case b would be 5. If your function's a constant, remember our limit is of the y values. So I always like to think of that argument in here on the limit as y equals whatever it is. So this would be y equals 5. This would be the function y equals 4x squared plus 3. You should know what these look like. This is the function y equals. This is the function y equals sine of x. So it makes quite a bit of sense if you think graphically of what y equals 5 looks like. So again, I'm going to reference the graphical to apply the analytic. So the function y equals 5 is a horizontal line through 5. So it makes sense that regardless of what the c is, whether it's 2 or whether it's -1, that the limit as we approach any constant of a constant function, I'm up on that line no matter what. So that would just be 5. I mean, I'm on a horizontal line, it's up at 5, so my y values are 5 everywhere. So if I were to say, what's the limit as x approaches 99 of 7? You'd say 7. Because my function's y equals 7, it's a horizontal line, so no matter where I hop on it, I'm always up at 7. All right, so our next one, we're on a parabola. We kind of know parabolas are continuous. They're lovely functions. I could split this up into the sum of the two functions from a previous section, but honestly, you just plug that in. If you get a nice number, that's where you are. So my limit would be at 4 times 2 squared plus 3, which is just, that's not very nice, plus sign, which is just at 19. Really what that means is on that parabola, 4x squared plus 3, if you were to graph it, right, and you could find its vertex and, it opens up. But if you were to graph it, as you approach 2 from both directions, you'd be up at 9. Okay, so I don't want to graph it. It doesn't interest me right now. But now watch what happens over here. Again, we just are going to just directly substitute this in, and if we get a nice answer, that nice answer is our nice answer. Do I get something nice when I do 1 squared plus 1 plus 4? And the answer is yes. I get 1 plus 1 plus 4, and that's a lovely 6. On the bottom, do I get a nice answer when I do 1 plus 1? The answer is yes, I get 2. So all things are nice. I get a 3. So this top thing is the world is lovely. Everything is nice. The sine wave. What is sine of pi halves? Well, there comes our unit circle into play, correct? What is the sine of pi over 2? Well, the sine and cosine of pi over 2 is kind of like 90 degrees, right? There it is. And sine is the y value. The y value is 1. And you should be able to think that through like that from your previous math classes and from our pre-skills. So that, guys, those are done. So now we're going to talk about, well, what if things aren't all nice? What if when I plug the -3 in on the top and I take that limit on the top and that limit on the bottom. Now notice when I take the limit on the top, I'm going to get a 9 minus 3 minus 6. I get a 0. When I do it on the bottom, I also get a 0. 0 over 0 is no good. It's called an indeterminate form. Some people would say, oh, it's something over itself, it's 1. I'd say no. Some people would say you can't divide by 0, it's infinity. I'd say no. Some people would say 0 divided by anything is 0, and I'd say no. But also I'd kind of say yes. So it's called an indeterminate form because it needs more work. You can't arrive at any concrete answer when your direct substitution gives you a 0 over 0. So one of the ways to combat that is to factor. So what I'm going to do is I'm going to factor the top. And I'm going to notice that that could be an x plus 3 and x minus 2 over an x plus 3. What that means is, see, this -3 gave me a 0 on the top and a 0 on the bottom. So I knew x plus 3 had to be on the top and on the bottom. The minute I cancel that, I've created an equivalent function that agrees with the original everywhere except at -3. What does that mean, LaRue? It agrees everywhere. It means that this original function, you might say, I don't know what the graph of it is. You now do. You now know it's the line x minus 2, right? So let's go say what this would be if I graphed it in decimals. I would enter y equals and I would graph it. And it's going to make the line x minus 2, which we know has a y-intercept of -2 and a slope of 1. And it's going to look like this. This is what your graphing calculator would make. Unless you zoomed in really carefully, you would also notice that when x is -3 and y is -5, there would be a hole in the graph. So it's a line with a hole in the graph. But the limit is still -5. So when I replug this in, I get a -5. My limit is -5, but there's a hole in the graph there. And we've talked about that, how the function need not exist at its limit. We are there from both directions. Even if the restaurant doesn't exist or it blew up, that's where we are. So when you factor and then you cancel, you're creating graphically a hole in the graph. So let's go look at this next one. When I put in a 1 on the top and a 1 on the bottom, can't have that, no good. What that means, though, is that there had to have been a factor of x minus 1 on the bottom, which I can see, and an x minus 1 on the top, which I couldn't see. And maybe you forgot how to factor cubics from Algebra 2 and pre-calc days, so I'm going to teach you how. All right, so I knew an x minus 1 had to come out. It was causing a 0 on the top and a 0 on the bottom. Well, even if you forgot like the model for it, and I don't like memorizing. I like to create things as I go. So I know I had to have an x squared as my first term. I know I have to have a plus 1 as my last term. I also know that the middle term had to cause canceling, so it's going to be the opposite, and then I multiply these two. Check it out. It's actually kind of cool. You learned it with A's and B's and you probably forgot it. So when I cancel these, right, and then I replug the 1 in to the function that's equivalent. So now I've got this quadratic, which is what this function is, and it agrees with the original everywhere except at 1. But, so it means there's going to be a hole at 1 comma what? 1 comma 3. Where's the 3 coming from? I now replug this in. My limit is 3. It means on this parabola, there is a hole at 1 comma 3, but we are up at 3. You might want to practice factoring some cubes, differences, and sums. That's what we did in class. So the first way to combat the 0 over 0 issue analytically is to factor and cancel. The next way is to work with conjugates. The trigger to that is seeing the square root, to be honest. When I put that 0 in on the top and the 0 on the bottom, I get this indeterminate form. We never say an answer is 0 over 0. We never say that equals 1 or it equals 0. We need to do more work. We basically need to get rid of the problem. The method of doing that when we see these roots is to multiply the top. Sorry, I'm gonna fix my iPad fell a little bit while I was writing. So we're gonna take that top, we're gonna take that bottom, we're gonna multiply it by the conjugate of where the root is. If it's on the bottom, the bottom. If it's on the top, in this case, the top. Well, what's a conjugate? A conjugate is the exact same setup. I like to parenthesize this. But we change the link between the two. Why do we do that? I like to talk about the whys instead of just the hows. Okay? So how do we do this? We multiply the top and the bottom by the conjugate of where that root is. Why does it work? Because when you multiply conjugates, you basically FOIL. But because we created these opposites, the O and the I cancel, the root disappears. So it just really cleans up our house. And this is really just 1. Like anything over itself is 1. So it's a huge technique in math that's used algebraically is we multiply by 1 disguised as something else. And in this case, I'm disguising 1 as the conjugate of my root expression in the numerator. Now watch what happens here. The reason the conjugate method is so sweet is because when I multiply these two, and we're not going to drop our limit because that's poor math grammar. So now I'm going to go to green. When I multiply my first, I just get an x plus 1. I get root x plus 1 quantitatively squared, gone. And then my outside and insides always cancel with conjugates, so I don't even really need to let my brain deal with that. And I get that. Super nice on the top because that's just x. Notice how clean that is and crisp. And then on the bottom, nothing's really getting any better, but you'll see what happens when I'm done. So when I'm up on the top here, what ends up happening is I get my limit. Don't drop that limit until you're all done. And on the top, I end up getting I'm having my limit as x approaches 0. I just have my x. I just have my x on the top because the 1's cancel. And then I have my x times root x plus 1 under the root plus 1. I'm kind of spreading out a lot here. My x's cancel. I have a 1 on the top. Now look what happens when I put the 0 in. I get this 1 on the top, and then I get the square root of 1 plus 1, which is 2, and this is my limit. Okay? There's a hole in the graph at 0, 1/2, but we are there. You could try graphing it in Desmos if you're having a hard time with the visual. In class, I'll probably do that, but these are video notes, and so I'm not. So number 1 technique is factor cancel if you can and replug. Number 2 is if you see these roots, conjugates are often helpful. Number 3 is the complex fraction issue. And so you'll notice again when I directly substitute the 0 in, I get 1/3 minus 1/3, which is 0 on the top, 0 on the bottom. This is an issue. So here's what we do. We are going to algebraically, that's what this section's on, is algebraic or analytical attacks to our limits. We are going to rewrite the numerator as a single fraction. So this kind of depends on how you were taught to add and subtract fractions. I personally like to do what I call the crisscross multiply across, or sometimes we call it crisscross applesauce method. So I multiply on the criss, I multiply on the cross, I apply the link between them. So just 3 minus x plus 3 all over, and then I multiply across. So I call it crisscross multiply across. Sometimes it morphs into crisscross applesauce, which sounds kind of weird, but then on the bottom I just get my x plus 3 times 3. But this is all divided by x. Now watch what happens when you take, for example, let's take 1/2 and divide it by 3. It's really 1/2 times the reciprocal, or 1/6. So really it's just 1/2, and then it collapses as a product. So instead of multiplying by the reciprocal 1 over x, it just ends up on the bottom. So I call it crisscross applesauce collapse as a product. Let's go try that over here just to make sure you kind of understand what I mean. If you had 1 over x plus 2, let's do it minus 1/2 over x, and you were cleaning that up. You would go criss, take the link, minus cross, all over, multiply across, or applesauce. That's the top. Collapse as a product. That's the bottom. And then you clean it up. All right, so back to our limit. That's Algebra 2 coming at you. And I didn't teach you Algebra 2, but that's the quickest way to do it. So let's see what we have here. We end up with, on the top, just a negative x, because the 3's are going to cancel. So we have our limit as x approaches 0. Notice I'm not dropping my limit of negative x over, I'm just going to put that out front, 3x times x plus 3. Now my x is canceled. There's where my problem was, because I know x being 0 was causing an issue on the bottom, so there had to have been an x of 0 on the top. I find it, I cancel it. I love math so much. So I end up with a negative 1 over 3 times x plus 3. So my original function, this, is equivalent to this everywhere except where x is 0. But that doesn't matter. It just means there's a hole there, but we'll still be there. Where will we be? Plug it in. Negative 1 over 3 times 3. That will be my limit. There'll be a hole on the graph at the point 0, comma, negative 1/9, but that's okay. I'm going to start this because this is one that a lot of kids struggle with. So for one like this, this is actually, you'll understand the significance of this in our next chapter, because this is leading into one of our next topics, which is on derivatives. But for now, if I plug in 0 for h, just trust me, I'm going to get 0 over 0 and have a big issue. When that happens in this x plus h kind of scenario, what you need to do is start expanding things. Again, you know h being 0 on the bottom is causing a 0 on the bottom, which means there's a singular factor of h on the top. You need to find it, factor it out, and cancel it. How do you find it? What you do is you expand that top. You have 4, and then you have x plus h squared. So you're just going to FOIL it. Firsts, outside and inside, would both be 2xh, and then you'd have your h squared. So I expanded the top. I'm just kind of writing it all out in its big expanded glory here. What's going to happen? I got to write it all out here. So watch what's going to happen here. I'm going to end up with a 4x squared from this, but I have a minus 4x squared over here. So that's going to cancel. Basically, what I'm going to tell you is everything without an h in it is going to cancel. Here's a minus 3x that doesn't have an h in it. Here's a plus 3x. Here's a plus 2. Here's a minus 2. Everything without an h in it cancels. Once you write that all out and you start doing your combining of like terms and canceling things. So what's left? You would have an 8xh from that. You would have a 4h squared. Sorry. And you would have a minus 3h. With our piecewise functions to find the limit, it's kind of nice to think of what it looks like graphically, but really what we have to do is we have to approach 2 from both directions. So we're going to approach it from the right. Where am I if I take the limit as x approaches 2 from the right of f of x? Well, I'm at 3 times 2 squared minus 1. 12 minus 1 is 11. When I approach from the left, I'm on the bottom piece of the piecewise. My limit as x approaches 2 from the left of the function is really just 5 times 2 plus 2, which is 12. Now, as I came in from the left and the right, these two do not agree, which means I'm going to have a jump in the graph there. Wherever that parabola left off in the line took over, there's a gap of 1. It doesn't even really matter how it looks. I'm just going to make a fake one. Wherever the parabola in the line changed off, there was a gap here. What that means is the limit does not exist. So you have to make sure that your left and your right approaches at this value are equal to say that the limit exists. That's it. Have a good one.